Monday because we really, it actually is, F2 and F3 are the same topic in the AP curriculum. So it's actually, I'm taking 3 days to do one topic from the AP curriculum. Like I was saying before I hit record, one of the things you'll have to do is look at the thing you're integrating and decide which of the things we've learned works. We're going to integrate using long division whenever we're in a situation where we see that we have polynomials in the numerator and the denominator, and the power is higher in the numerator. As a matter of fact, the power is higher in the numerator, and in most cases, the thing in the denominator is linear. Now, I said most cases because you can see over here in example C, that is not linear. So in most cases, you'll have something linear in the denominator. The thing about it is you'll see when we actually go to the integrating, we kind of need to have only a handful of things in the denominator that actually work. That x squared plus 1 is the denominator of arctan when we integrate. When we integrate and get arctan, it happens when we have x squared plus 1 in the denominator. So that's really the only reason I'm allowed to use something not linear here and actually get an answer that we can do with what we know. So what we're going to do, I'm going to kind of go from example 1 to example 2. I found that this kind of got a little bit weird when I just went across example 1 and then jumped to example 2. So we'll do part A in example 1, which is just doing the division. And then we'll jump down to example 2 and actually integrate. So you have a couple options when you're doing long division. One of them is synthetic division. And that works when you have an x plus or an x minus. There are ways to do it with letter B, but I don't want to get too into the weeds. So if you have an x plus or an x minus, use synthetic division. You don't have to. If I shouldn't say you can use synthetic division. I'm fine if you still do long division with this. If that's just more your comfort level, you're going to get the same result. Synthetic division is a shortcut for long division, but there are some little things that you have to remember along the way. And the very first thing that you have to remember is you're going to take that number that you're dividing by, or the number that you see when you look at the denominator, -5, and you're going to flip its sign. So when you do synthetic division, you are going to put the opposite sign on the outside. So if it's a -5, you'll put a +5. And then you're going to drop the coefficients from the numerator into the bar. So 1, -6, 7, and -15. Be careful if there's a missing term, you need to have a 0 to place hold. So if like this -6x squared wasn't here, and I just had x cubed plus 7x, there would need to be a 0 down here. Okay, so just be careful about that. You do need zeros to place hold missing terms. And then we just bring down the first coefficient and we multiply 5 times 1 and put that result right here. Then we add down the column. -6 plus 5 is -1. And we multiply and put our answer there. 7 minus 5 is 2. We multiply and put our answer there. And -5 plus 10 is -5. That last number is our remainder. So if you remember doing this in pre-calc or even maybe Algebra 2, not sure. If you remember doing this, when you got the 0 there, the thing divided evenly, and when you had a remainder, you had to deal with it. So what's our answer? What's the simplified, what do we get when we divide that numerator by that denominator? What is the simplified version of that fraction? Yep. Minus 5 over x minus 5. Yep. I mean, and what we're doing with the remainder is equivalent to what we do with the remainder when we when we just do division with regular numbers, back from elementary school. But it is equivalent because if you were dividing something by 3 and you had a remainder of 2, you'd put plus 2/3, or you'd have 2/3 at the end of your number. So this is equivalent to what we do with regular numbers. So the idea here is that if this is the thing you need to integrate and it's equivalent to this, you've got 4 things to integrate. Power rule, power rule, power rule, power rule? No, because it's to the first power. So this one's going to give you the ln. Yeah, this is a linear shift of 5 over x. That might not be the most accurate statement in the world, but for the way we think about things, this is a linear shift of 5 over x. A horizontal shift of 5 over x, so it works just like 5 over x for the way that we think about it. Okay, so let's go down to letter A and actually integrate that thing. In the process of seeing this integral, you've looked at it and said, hey, I've got a linear denominator and my powers are higher in the numerator. This sure is an integral where I have to do long division to solve. So then I do the long division and I say that this integral is the same thing as the integral of x squared minus x plus 2 minus 5 over x minus 5. Thank you, dx. And then I apply the power rule, x cubed over 3 minus x squared over 2 plus 2x minus 5 ln absolute value x minus 5 plus c. The only time it's ln is when your thing is being raised to the first power in the denominator. So you have no exponent, really. You don't see an exponent. But yeah. Make sense? Okay. Let's take a look at letter B. There is a way to do synthetic division when you have a coefficient in front of your x, but I feel like it's a bunch of rules that I have to reteach myself every time I do it. So I'm not going to do it. And I'm going to do this one with long division. So we end up with 4x plus 5 for x cubed minus 7x squared minus 11x plus 2. There we go. And it is the same long division you did in elementary school. You ask yourself, how many times does 4x go into 4x cubed? X squared times. Yeah, what do I have to multiply 4x to get 4x cubed? And that answer is x squared. For the most part, your coefficients should work out pretty nice with these. If you start finding like weird things happening, you're doing something wrong. And they've set the problem up that way, because if you get numbers that don't go into each other easily, the whole thing just becomes a tedious exercise in calculation, which usually isn't the goal of a problem like this. So that gives us 4x cubed plus 5x squared. But then we have to change those signs. So this is how I always show it, because we need to subtract those things. Cancels. And again, kind of seeing I'm doing the right thing. When I do negative 7 minus 5, I get negative 12 x squared. And I'm expecting to get a multiple of 4 here, because my next thing to ask myself is how many times does 4x go into 12x squared? If I got an 11 here or a 2 here, 2 might not be the worst thing in the world, but I would be, start questioning myself. Did I make a mistake? Bring down one more term, since you're going to have, when you multiply this next one, you're going to have a binomial. So we'll bring down our 11x. Ask ourselves the same questions. How many times does 4x go into negative 12x squared? Negative 3x. So I will write the negative 3x there, which gives me negative 12x squared and minus 15x. Both of those signs need to change because I'm subtracting. Actually, I could just do it this way. Just right over the minus. What's that? Yeah, so you're subtracting there. What you need to do is you multiply that and then you take that away. So when you take that away, both signs change. So they both become pluses. The thing we see at the end is making sense because we end up with a negative 4x, right? No, positive 4x. Yep. Cool. And then we bring down our 2. And then the easiest question, how many times does 4x go into 4x? 1 time. Gives us 4x minus, or plus 5. I'm a step ahead of myself. Change my signs. And I end up with a remainder of 2 plus negative 3. Yep. So we'll put minus 3 over 4x plus 5. Cool. All right. So just like I said on the last problem, you've looked at this integral. You've learned a whole bunch of different things to do. You've identified the linear denominator. That's a giveaway, not a guarantee, but a giveaway. And the higher powered numerator, and you said, oh, long division. So you did the long division. And now you have the integral. I don't have enough room on my screen for it. X squared minus 3x plus 1 minus 3 over 4x plus 5 dx. Which is really similar to what we did on the last one. We've got x cubed over 3 minus 3x squared over 2 plus x minus what's my coefficient here? Not just negative 3. Not negative 12, right idea, but we're integrating. Yes, negative 3 over 4. So the linear chain rule, and I could show this with U sub too. I'll take a minute down at the bottom and show this with U sub. This will actually end up being negative 3 over 4 ln absolute value of 4x plus 5 plus c. And again, if you think you're not going to get that right coefficient, then you should separately look at the integral of 3 over 4x plus 5. I'll just keep it positive, dx. My u is 4x plus 5, which makes my du 4 dx. But I don't have a 4 dx. I have a 3 dx. Yep. Yep, you multiply by 3/4. So 3/4 of du equals 3 dx. So the integral we're solving is 3/4 the integral of 1 over u du. And that's where that coefficient comes from. So that's 3/4 ln absolute value of u. And that's where the 3/4 ln 4x plus 5 comes in. So linear chain rule is great when you see it. When it drops itself in here somewhere like this, U sub does the exact same thing. U sub is just there. Whenever you're working with something linear, U sub is just sort of the long way of figuring out that coefficient. But if you're more accurate with it, then the long way is the better way. So yeah. All righty. And letter C. We'll jump back up to the division part. I shouldn't say there is none, because I'm sure if you've thought about it long enough, you can find one. But there's no easy way to do that with synthetic division because the denominator is not linear. So we will divide our numerator by x squared plus 1. And we have a situation here where we do need to placehold. We have 3x cubed plus 0x squared plus 2x plus 5. What do I have to multiply x squared by to give me 3x cubed? 3x, yep. That gives us 3x cubed plus 3x. And maybe this isn't as, yeah, I actually might end up, I actually think I'm going to end up here okay without the, maybe without the placeholder, but the placeholder was a good idea nonetheless. Yeah, subtract them both. That is going to give me negative x plus 5. Can x squared go into negative x? No. So our answer is actually going to be 3x plus negative x plus 5 over x squared plus 1. Careful not to move. If you were going to move that negative down there, you would also have to switch 5's sign to be algebraically correct. So in this situation, I think it's just better to make it negative x plus 5. Don't get fancy. All right. Okay. So now this one here is kind of designed to be the most complicated example I could give you, because when we go to do that integral, let's take a look. Integral of 3x plus negative x plus 5 over x squared plus 1 dx. This is going to give me 3 halves x squared plus the integral. Let's just this time negative x plus 5 over x squared plus 1 dx. So we'll just focus on the fractional integral on that one. Can I do u sub to do this integral? Because that's usually your first thought. Yeah, good point. You would never just use x because you're not changing anything when you use x. You're just changing the letter. Yeah. Well, I would think the only thing I would use here would be x squared plus 1. That the problem is the plus 5. Yeah. So the negative isn't the problem. The problem is the plus 5 here. So if I said u was x squared plus 1, du would be 2x dx. But I have this x plus 5. You're not going to be able to move that plus 5 in there. It's not going to work. But the fact that I do have an x here, the option that we have is to split and make two separate fractions, negative x over x squared plus 1, which u sub will now work on because du will be 2x dx, x, then I have an x dx. And then the second fraction will be 5 over x squared plus 1, which is a must know. It's arctan, but with a 5 in the numerator. So we're actually going to have two separate integrals to solve here. This one gives me 3 halves x squared plus, well, I guess I can do it this way. This is not partial fractions, no. Yep. Minus the integral of x over x squared plus 1 plus the integral of 5 over x squared plus 1. We do need dx on both of them. Yep. Dx, dx. And both of those integrals can be done. Let's separately do x over x squared plus 1 down at the bottom here. So the integral of x over x squared plus 1. Make u our denominator, x squared plus 1, which makes our du 2x. Put my dx in there. As I always say, 2x dx. Boom. We don't have 2x dx, we just have x dx. So we divide by 2. So now to make an algebraically equivalent integral, we put that 1/2 out front, we put the du out front, and that du has taken up the x, so we just need a 1 to placehold, and we have a u in our denominator. So this integral comes out to 1/2 Yeah, ln u for the moment. Ln absolute value of u. So now we can plug that right in there. So we have 3/2 x squared minus 1/2 ln absolute value of x squared plus 1 and those absolute value bars are serving no purpose because x squared plus 1 will never be negative, but they're fine to be there, plus 5 arctan of x squared plus 1 plus c. Yep. So yeah. So purpose, I wanted to really show everything that they can throw at you there. A technique all in itself of splitting up, the numerator of a fraction because one can be u subbed and one's a must know. All right. So a little bit over 25 minutes to get as much of this done as possible. Yes. Sure.